Our last lesson was a review of the setup and definition of Riemann integrability for bounded scalar-valued functions of one variable. In this lesson, what we're going to do is take all the same notions and generalize them for functions which are bounded and scalar-valued, just like they were before, but now the domain is going to be some subset A of n-dimensional Euclidean space. Everything generalizes in a way which I think is really natural. So this video might actually be pretty short, and by the end we will have a working definition of Riemann integrability for such functions. Okay, so let me start by just taking things that we already know how to work with and saying what the natural generalization into the new domain will be. When we integrate functions of one variable, typically we're interested in integrating them over closed bounded intervals of the form a to b. Now, this is the most interesting thing about our generalization for functions of multiple variables, and that is that we're still going to consider bounded domains. We'll typically call them A. But now A isn't going to be necessarily as nice and kind of rectangular looking as, say, a closed bounded interval. So you can imagine that A is some weird shape like this. And that's going to give us some interesting things to think about as we talk about integrability for functions. Okay, so from bounded closed domains of this form to just general bounded sets A, then the next thing we're going to do is say, okay, and we'll go through this with a lot of pictures in just a moment. Because this is such a strange shape, how we will set up integrability is we will enclose it in what I will refer to as a nice rectangle. That sounds non-technical, but let me give it a technical definition, which I've written down here. And that is that this rectangle S, enclosing this original domain A, whoops, I meant to write that in green, is going to be a rectangle in the appropriate dimension so that the sides are parallel to the coordinate axes. Okay, the domain A that I sketched here is flat, so we can imagine that this is a subset of R2. That means that my rectangle here is really truly a rectangle. Like a child would look at this and call it a rectangle. The side here is parallel to the x-axis. This side is parallel to the y-axis. We can generalize that to what I would like for us to continue to call a rectangle. But when I say rectangle in the domain, I'm talking about an n-dimensional rectangle. If we were working with a domain in R3, you would maybe want to call it, outside of math class, a rectangular cube or something like that, but we will still call it a rectangle. And then the sides of the rectangle are written this way, meaning this is like an interval on the x-axis, this is an interval on the y-axis, an interval on the z-axis, or actually however many coordinates we have. By writing it as this Cartesian product of closed bounded intervals, we're saying that the sides are parallel to the coordinate axes. It's just the easiest type of rectangle for us to work with. Okay, so to recap, we have a bounded set A, which is a subset of Rn. We're going to take it and enclose it in a rectangle that we will name S. I'm going to call it S whenever I can. I used to call these R, but then I thought if I say R out loud, it sounds like real numbers R. So if I write R at any point, please forgive me. S, this enclosing rectangle, it is also a closed bounded rectangle. It's an n-dimensional rectangle, and we can write it as a Cartesian product of intervals that indicates to us that its sides are parallel to the coordinate axes. We define the volume of such a rectangle to be the product of its side lengths. So if this side was A1, B1, the width of this side is B1 minus A1. And if this side went from A2 on, say, the y-axis to B2, then its side length is B2 minus A2. And the volume of this rectangle is this length times that length, and that's what we are generalizing here. Okay, we have to be careful as we talk about these objects because we have our working childhood vocabulary, and then we have vocabulary for this unit. Again, we're always going to call it a rectangle, even if it's not truly a rectangle, like an n-dimensional rectangle. We'll still use the word rectangle. And then we will also use the word volume for this kind of shape that we might have in R2. So if you're looking at this really, truly proper rectangle, you might want to say, well, its area is the product of this length times that length. But in general, I'm going to use the word volume. Okay, and then we will, and I'm going to go through this with pictures in just a moment, but let me give you a quick preview of what's about to happen. We will take the sides of the enclosing rectangle and chop them up just like we chop up intervals when we look at integration of with respect to one variable. So I'm going to imagine partitioning, say, this side, and I tried to do it in a way so that these interval widths are not consistent. And we can partition this side too. In fact, we will. Doesn't have to be the same number of slices. They don't have to be evenly spaced. I'm regretting how many slices I made here, but you can imagine that if you extended this across, you would generate a grid. Okay, picture's getting kind of horrible now, but imagine I keep going with this. We generate a grid of n-dimensional rectangles. I won't call this grid in general, just for this particular picture, it looks like a grid. And this subrectangle generated by our partition is what I'm referring to here. So we will have subrectangles. In the past, I used to call these R sub I. I'm going to try to call them S sub I from now on. When we looked at integration for functions of one variable, we talked about subintervals. Here, the analogous notion is going to be these subrectangles. Notice these subrectangles are also n-dimensional rectangles. They have the same kind of qualities as S, right? So if S is an n-dimensional rectangle in Rn, so is S sub I. It's just kind of inside of S, but it's the same type of rectangle. So it has the same kind of volume. The volume of the subrectangle is going to be the product of its side widths. And so we would do that, say, perhaps for each of these subrectangles. Notation will bring in this Greek letter nu down here, and that is going to go into our construction of upper sums and lower sums in just a moment. So when we wrote upper and lower sums of a function with respect to a given partition, we had that width factor that we wrote as delta xi. Now we're going to start writing this as nu of si, where that means the volume of the ith subrectangle, and it comes from taking the product of the side widths, just like it did here. Okay, one more remark I want to make about these subrectangles before we move on, and I'm going to basically go back through all of these ideas, but with a much nicer picture than this one. And that is that when you subdivide all of the sides of your enclosing rectangle S, you create what in this picture would make sense to call a grid of subrectangles. And there can be a lot, and you could come up with some systematic way of indexing them. For this particular context, I might actually index these with two subscripts, say I and j, where I takes me along the x axis and j takes me along the y axis. That would be a natural way to index through these subrectangles. However, regardless of the partition, once you have made a partition, there are only ever a finite number of subrectangles. So just like before, if you chop up an interval using some partition, so you slice into it, you create a finite number of subintervals. Here it's a finite number of subrectangles, which means that if I do something like add up across all of the subrectangles, I often just index them with one index, and that's going to run me from, say, subrectangle number 1 through whatever the last one is. So in this case, I could just stick with this single subscript where this is like S1, 2, 3, 4, 5, 6, 7, 8, 9, whatever. And then we just come up here and keep going with the same subscript. You might not like that. You might want to do Sij for R2, Ijk for R3. But again, it's a finite collection of subrectangles. So I usually just say we have a finite family of subrectangles, and now we're going to construct some sum across the total number of subrectangles, which is, again, finite. Okay, I think I will stop this discussion here and we will look at some pictures. Now what I would like for us to do is work back through our understanding of the terminology that we just looked at, this time with pictures that are a little bit better. And what we will build up is our definition of Riemann integrability. So here we have a function f, which is a scalar-valued function of two variables, which is bounded over a bounded subset A, which is a subset of R2. The picture, of course, has to be in R2 because that's the only one that we can draw, but imagine that this is a subset of Rn, and f is a scalar-valued function of n variables. We want to think as generally as we can. Again, f is bounded, A is bounded. In this particular graphic, I drew f as if it were continuous, but that doesn't have to be the case. It's just hard for me to sketch a non-continuous function in R3. Okay, so we have the graph of this function, and what we're going to do is take that domain A, which is sort of peanut-shaped, and enclose it in a nice rectangle S whose sides are parallel to the coordinate axes. So we want to think of S as the Cartesian product of intervals. In the picture, it's two intervals, one along the x-axis and one along the y-axis. Okay, so we took A, we enclosed it in this nice rectangle S, and then what we're going to do is extend our function f so that it's defined not only on A, but on S. It's quite possible, and often happens, that your function f might be defined on all of Rn, but you're only interested in integrating it on the original domain A. In order to precisely define Riemann integration, we want to work over a rectangular domain. So again, this is just formalizing the idea that we're only interested in f over A, so we zero it out outside of A. So I write this as this kind of formal extension, but the idea again is keep f as it is over A and then just zero it out outside of A. Okay, hopefully you're with me. I filled in this diagram here in pink so that it matches the color. So everything that's pink here is the graph of f. It just so happens that it's flat when it's inside of S but outside of A. Okay, now that we have our function defined on the entire domain S, because we basically broadened our domain from A to S, what we're going to do is partition S. So formally, what I've done here to create this partition is sliced along the x-axis, sliced along the y-axis to generate this subrectangle collection that subdivides our original domain S, or rather the extended domain, into a family of subrectangles. Let me take a moment just to tell you how to write a notation for this partition. If this partition was named P, then what we could say is it is the Cartesian product of a partition along the x-axis and a partition along the y-axis. So you could literally say, x, let me write it as A1 equals x naught. That refers to like this smallest x value here on it's the left side of the domain along the x-axis. And then my next slice on the x-axis is x1. And we keep going x2, x3, x4, all the way until we get to however many sub-intervals we've divided the x-axis segment into. Let's call that N1. And that, of course, is going to land us on the right endpoint for the x-axis, and that's B1. Okay, so these are the slices along the x-axis, and then we're going to take the Cartesian product of this set of points with another set of points, and that's the slices along the y-axis. So let me do that a little faster. This is a Cartesian product. It's not the variable x. Sorry, it confused me for just a second there when I saw it. Okay, Cartesian product with the set that looks like A2, which is like the smallest y point over here, and then y1, y2, all the way through. Doesn't have to be the same number of subintervals along the x and y axis or however many coordinate axes you are considering. So let me call this y sub n2. So I might have 10 points here, in which case this would be x sub 10, and 20 points here, and this would be y sub 20. But the idea is that the Cartesian product, so this formal product of these two sets of points, generates these subrectangles that we've subdivided S into. Okay, so now we have this partition of the rectangular domain S, and there are a couple of things for you to notice that we will kind of dive more into with future lectures, and that is that there are different types of subrectangles here in terms of how they relate to the original function f. Out here, for this subrectangle, this is just a subrectangle of the exterior of A, meaning f is entirely 0 out here. On the other hand, here we have a subrectangle which lives entirely inside of the original domain A. So here it's like we're going to consider f over this entire subrectangle. And then we have something that's special about integrating for a domain which is higher dimensional. So this is something we don't really talk that much about when we look at single variable calculus. And that is this subrectangle here has some of A and some of the exterior of A. In some ways, I took a function which was continuous. So my original graph here was the graph of a continuous function, and I've ripped it along its boundary so that when I think of that function now as a function over S, it's no longer continuous because I've added this curve of discontinuities in my new domain S. So again, this is something that we're going to discuss. I'm not going to go further down that road in this particular lecture. I just wanted to point it out to you that we start to see some interesting things here that we don't see that much of when we talk about single variable calculus. So usually with single variable calculus, we don't have very pathological domains or just interesting domains, and we do in higher dimensional domains. And it leads us to some really interesting things. Okay, next what we're going to do is say, just like we did before, take, say, this subrectangle, maybe the nicest of the three that I indicated because it's under our original function f, it's part of the original domain A. I want to imagine the analog of like the sup of f times delta xi, right? So that was how we set up, say, an upper sum or lower sum, or upper sum specifically, we're talking about sup, of our function with respect to a given partition. Okay, it's a little hard to picture, but the sup of f might be like here, and delta xi is that notion will turn into the volume of the subrectangle base. When we multiply the volume of the subrectangular base with the sup of the function, I can't really tell in this picture if I drew an accurate sup or not, what we get is an n+1 dimensional volume. There are some areas where we have to be careful because we have volume of the base and we have this kind of volume as well. Just identify the dimension of the volume that you're talking about. Down here, it would be n-dimensional if our domain A was a subset of Rn. And then this prism in the picture that we generate is also a volume, but it's an n+1 dimensional volume. But it's like a prism, so its volume is base times height. So it's the original volume of the base, the n-dimensional volume, times this height that we've identified, and that is the sup of this function over this particular subrectangle. Okay, so if we wanted to make now the upper sum, yes, I'm like upper integral or upper sum of f with respect to this partition, what we would do is make this kind of prism for each subrectangle. So for each of these subrectangles here, I'm going to have the volume of the base, the n-dimensional volume of the base, times the sup of the function's outputs over the respective subrectangle. Here, that's going to be 0. Add them up across the number of subrectangles generated by this partition, and it gives us the exact same concept of an upper sum as we had before, likewise a lower sum. So what I would like for you to do is just pause this video for a moment and see if you can write down the upper sum and lower sum of f with respect to this partition, again, taking what we had before in the previous lecture and just generalizing it for this new context. Hopefully this is what you wrote down. So the upper sum of f with respect to the partition we were just looking at is the sum over all of the rectangles generated by the partition. And this is how I will typically index it because, as I said a while ago, it's always a finite collection of rectangles. So while you might imagine trying to indicate a sense of direction with subscripts I, j, k, etc., it's not really necessary because you're only ever doing a finite sum here. So I'm just going to number them however I want to. And then it's adding up a bunch of products where this first term, the sup, we think of that as a height. And then the second term is the base volume. So that overall, by identifying the sup as our choice of height over each subrectangle, what we are adding up here is a bunch of tall prism volumes. So let me say sum of, I'll add in here the word signed in case the sup is negative. We picked the sup, so these are the tall prisms in Rn+1. Prism volumes. Okay, so for functions of one variable, we talked about tall rectangles. Now we're talking about tall prisms. And I included here the word signed again, just in case those prisms drop below what in the previous picture looked like the xy plane. It would still be a geometric notion of volume, but it could pick up a negative sign. Let me remark here that when I say the word volume, volume is always a scalar. So the volume is a number. This is a number. This is a number. We multiply them together. We get a number. We add them up. We get another number. So when I say n-dimensional volume or n+1 dimensional volume, the volume is a scalar, but I'm talking about what it is the volume of, like the ambient setting for the relevant object. So if I say an n+1 dimensional volume, I'm talking about it's the volume of an object which lives in Rn+1. Okay, so this is a pure scalar. F is scalar valued. We're taking the soup of a bunch of function outputs, so these are scalars. This is also a scalar. It represents volumes of objects in Rn, specifically the volumes of the bases formed by our partition. We add them up, and geometrically, what we're imagining are prisms in Rn+1, because we have the base here, and then we give it a height, so that gives us this extra direction to travel in. And they are volumes, so this is going to be a scalar, but it's measuring volumes of objects which live in Rn+1. Okay, I think you've got it. So let's move on to the lower sum of F with respect to the same partition. Exact same idea, except our height here is going to be short heights. So that overall, this is going to be the sum of signed short prism volumes. I won't write that down. Exact same notion, except instead of taking tall heights, we're taking short heights. Okay. Again, I hope that despite, maybe some clarifying remarks I was making, I hope they didn't make it more confusing. This really should feel exactly like the type of Riemann integration that we were doing in the previous lecture when we looked at functions of one variable. The only difference here is really in this term, but again, that's not that difficult in the setup. We will have interesting things to talk about because the domain A can be so interesting in its own right. But this idea hopefully is clear. Again, test your instincts by pausing the video. See now if you can define the upper integral, the lower integral of F over A, and then, propose what it means to say that F is Riemann integrable over A. All of these definitions and statements look almost exactly like what we wrote down in the previous lesson looking at functions of one variable. So hopefully this is very close to what you've written down on your own paper. The only thing that's stopping it from being exactly like what we had in the previous lesson is this idea that first you take A and you enclose it in some nice rectangle S whose sides are parallel to the coordinate axes. Here, I've written this as if you pick an S. You could actually generalize this set to say any possible S, which properly encloses A according to our requirements. I'll leave it to you to work through the details that it doesn't matter exactly what S looks like, so long as it's a nice rectangle with sides parallel to the coordinate axes, which contains A. And a working understanding of why it doesn't matter is because we extend F to be 0 off of A. So if I pick this rectangle and you pick something slightly larger, any extra domain between my rectangle and your rectangle, that's where the function is going to be 0, or the function will be 0 there. So it won't change our numbers, basically. Okay, so given this kind of precision that we have to make here, we will define the upper integral of F over the domain A to be the infimum of all possible upper sums of F with respect to all possible partitions. It's the exact same idea as before. We have uncountably many different ways to partition a suitable enclosing rectangle. Just like before, you can prove that the set of upper sums is bounded below. It's basically the exact same proof. Therefore, it has an infimum, and that infimum is what we call the upper integral. Likewise, the lower integral, consider all possible lower sums of F, generated by all possible partitions, uncountably many partitions. That set, just like before, almost the exact same proof is bounded above, so it has a supremum. That is what we call the lower integral. I don't have a great animation and MATLAB or anything illustrating these ideas, but it's the same geometric understanding as before. As if we get better and better, more and more refined partitions, we imagine our upper sums come down and our lower sums come up. And what our upper sums are kind of coming down to, what they might be approaching, is this upper integral value. So this is a number. Likewise, our lower sums, imagine a bunch of different kind of short prisms. If you could refine better and better and better to kind of bring those prisms up, they feel like they're limiting towards something, and that's this lower integral. Those two lines exist for any bounded function over A. So you could do this for any bounded function, including wild-looking functions with lots of discontinuity, so long as they're bounded. Riemann integrability happens, though, when those two numbers coincide. So if your upper integral and your lower integral are the same number, that's when we say we have a Riemann integrable function. Exact same idea as before. And just like before, exact same theorem, I didn't change anything here. We say that since considering all possible partitions is not tractable. A common approach to proving integrability is to use Riemann's condition for integrability. Take the domain A, enclose it in some suitable rectangle S. Can you find, for a choice of epsilon greater than 0, just one good partition of S? Call it piece of epsilon, just to give it a name, so that the gap between the overestimate and the lower estimate, or the upper sum of F with respect to your very good partition and your lower sum with respect to the same partition, that's within distance epsilon of each other. Because if it is, it's like you're saying that these two numbers can be squeezed arbitrarily close together. Therefore, they're going to coincide. Okay, that wraps up this lesson. We didn't really do much in this lesson. What we did was we took everything from the previous lesson and just generalized it and kind of established it for domains which are going to be higher dimensional. Coming up, we will start to think more about how to kind of understand the domains that we're looking at. Because as I've mentioned, the domain A is going to bring in some new notions that we didn't have before. So we will spend some time actually just thinking about how to study A.